Hello, greetings, and welcome. This set of notes marks the beginning of Chapter 2, where we'll study the PVT phase behavior of fluids. Okay, so PVT phase behavior of fluids. What are we doing? Right? This is a course of engineering thermodynamics. Okay. So in Chapter 3, we will introduce the first law of thermodynamics and begin solving what you might think of as engineering thermodynamics problems. The focus of this chapter is on reading and modeling the PVT phase behavior of fluids. Right? The reason being, as we first mentioned in Chapter 1, if I have a single component, single phase system, so pure water and a piston, I have 2 degrees of freedom. Right? If I specify 2 intensive properties, all other properties are fixed. Okay? As mentioned already, our favorite 3 intensive properties to work with are pressure, volume, and temperature. Why? Because pressure, volume, and temperature are physical quantities that I know, understand, and can readily measure in the laboratory. Okay, so pressure, volume, temperature are our favorite 3 independent properties to work with. Okay, we only need to specify 2 of those for a single component, single phase system, at which point everything else is fixed. So in this chapter, okay, before we move on to solving problems in Chapter 3, solving first law, engineering thermodynamics problems in Chapter 3, we first need to become comfortable working with pressure, volume, and temperature phase diagrams. Okay. A second major part of this chapter. All right, so the first set of notes we'll look at PVT phase diagrams, and the next set of notes we'll start to move on to modeling. Right, so we want to be able to quantitatively model the PVT phase behavior of our problem, or PVT phase behavior of our fluids, so that we can quantitatively work through and solve problems beginning in Chapter 3. Okay, so in this set of notes we'll work on PVT phase diagrams, and then we'll move on from there on how to quantitatively model. Okay, and we'll talk more about that beginning in the second set of notes. Okay. And so I will try and work through the notes here in a slightly different way, where I'll try and mark them up as if we were having some good conversation in class. All right, so the first thing I want to mention again is in Chapter 1 I had mentioned the Gibbs phase rule. Okay. Again, in the textbook up to this point there's no mention of the Gibbs phase rule. The Gibbs phase rule isn't introduced and isn't derived into, I believe it's Chapter 8 in the second half of this course, or what would be the second half of this course. But I want to introduce it here just because it's very convenient, or very good reference to have in your head as you work through problems, as you read phase diagrams, as we go to solve problems, just trying to take inventory as to whether or not we have enough information. Okay. So the Gibbs phase rule, tells us the number of independent intensive properties that need to be specified to fix unambiguously the thermodynamic state of my system. All right, so here I have it in boxed in. F, the number of degrees of freedom, is equal to n. Okay, n is the number of components, minus pi, the number of phases, plus 2. So if I have a single component, single phase system, right, n would be 1, pi would be 1, so I have F equals 2. All right, so that gets us back to the case if I specify, if I have a single component, single phase system, I have 2 degrees of freedom. Okay, so I have 2 intensive properties that I need to be specified to fix that state of my system. So if I specify just temperature and pressure, everything else is fixed. All right, so Gibbs phase rule, all right, for a single component, single phase system, tells us I have 2 degrees of freedom. Say temperature and pressure, pressure and volume. All right, your choice. Okay, but key is once 2 is fixed, once 2 are specified, all others are fixed. If I have a single component 2-phase system, so water at vapor-liquid coexistence, then n is 1. Okay. Pi now is 2, all right, so n minus pi plus 2 is 1. So if I say I have water at vapor-liquid coexistence, then I need just 1 degree of freedom to pin down the state of that system. Okay, maybe it's temperature, maybe it's pressure, right? So at 1 atmosphere, right, I know that corresponding boiling point is 100 degrees C, right? That temperature is fixed, is known. Okay, so that's the Gibbs phase rule. Okay, I only mention it or bring it up so that we can use it as we work through our problems, right? To take inventory of, do I have enough information, and just to try and make sense of everything. Okay. All right, so we said, or I've mentioned a couple times already, okay, so thinking again in terms of single component, single phase system, I have 2 degrees of freedom. right? I could choose any intensive properties to pin down the state of my system. My favorite are pressure, volume, and temperature, right? And when I say volume, right, to be clear, right, I'm referring to an intensive volume. So either specific volume or molar volume, okay? So PV and T are my favorites because they're physical properties I know, understand, and can readily measure. All right, I know temperature. I can measure temperature with a thermometer. I know what pressure is. All right, I can physically measure it using a barometer. And molar volume, right? I can measure the volume, and if I say can calculate the mass of my substance, I can calculate a specific volume. Okay. All right. So single component, single phase. I have 2 degrees of freedom. So pressure, volume, temperature, right? I could plot out the PVT phase behavior of my system in a 3-dimensional surface like this. But if I think of this case of single component, single phase, I have just 2 degrees of freedom. And so what we normally do is we just look at 2-dimensional planes of our 3-dimensional surface, right? Since I only need, for that case, 2 degrees of freedom to characterize my system. Okay, so it's easier to think in terms of 2D. It's easier to plot, right, my phase behavior in terms of 2-dimensional surface, and that's all I really need since I only have 2 degrees of freedom. Okay, where again, pressure, volume, and temperature are our favorite variables to work with. All right, last note before we start to look at faces of that PVT surface. As we talked about Gibbs phase rule, the last concept I want to remind ourselves of from chapter 1 is this idea of mechanical and thermal equilibrium. Okay, so mainly in terms of thinking about systems at vapor-liquid coexistence. Okay, so if I have water at vapor-liquid coexistence, okay, the criteria of mechanical equilibrium tells us that the pressure of those 2 phases are the same. Right, if they have those 2 phases in equilibrium, those 2 phases are at the same pressure. Thermal equilibrium tells us that the temperature of those 2 phases are the same. Okay, and then chemical equilibrium would be that the chemical potential, or for a pure component system, molar Gibbs free energy of those 2 phases are the same. Okay, the main ones that we want to think about, since we're looking at PVT phase diagrams, or phase diagrams in a PVT surface, are this idea of mechanical and thermal equilibrium. If I have 2 phases at coexistence, they're going to be at the same temperature and same pressure. Okay. All right, so what we're going to do next, all right, is, again, I could plot, right, my phase behavior in 3-dimensional space using, pressure, volume, and temperature, right, using my, with respect to these 3 variables. Okay. But again, single component, single phase, I have just 2 degrees of freedom, 2 variables that need to be specified to pin down the state of my system. So that, in addition to just being much easier to think and then plot data in 2 dimensions, we're going to look at the faces of this phase diagram. Okay, so the first one that we're going to look at is pressure versus volume, and then we'll look at pressure versus temperature. Okay, so we're going to start by looking at this first face here. All right, so here's my PV graph. Okay, so again, it's just much easier in terms of thinking and working in terms of 2 dimensions. So the first thing I want to point out is when I look at my PV phase diagram, okay, the first characteristic that you should notice is you have this dome. Okay, so this dome here, right, so this black line, okay, so I'm going to try not to color the whole thing, but this black line here, okay, well, I guess if I try and color it, so if I can try and highlight this black dome, okay, this corresponds to my phase envelope. Okay, what do I mean by that? Okay, well, underneath the dome would correspond to a system at vapor-liquid coexistence. Okay, what do I mean by that? I have some closed beaker, okay, of some known volume, and I add some mass of water to that beaker. Okay. If the molar volume puts me underneath the dome, right? So if I measure the specific volume, right, volume per mass, and let's just say it puts me at point D, okay, this would correspond to a point underneath my dome that would tell me that my system's at 2-phase coexistence. Okay, what'll happen is we said at 2-phase coexistence, or if at vapor-liquid coexistence, my 2 phases are at the same pressure. So what happens is I get phase splitting along an isobar, right? So what I mean by that is here's pressure, here's volume. So if the specific volume of my system puts me here, okay, underneath the dome, okay, I will get phase splitting. Okay, and what I'm doing here is I'm just drawing a line across my phase diagram of constant pressure, because I know that my vapor and liquid at equilibrium will be at the same pressure. Okay, and what I do is I just read across, right, and the point where I hit my left lobe, okay, that's going to correspond to my liquid phase. Where I hit my right lobe, right, that's going to correspond to my vapor phase. Okay, so if I have a point underneath the dome, I get phase splitting along an isobar. Okay, and that from that isobar, I'm going to have a liquid in equilibrium with the vapor. Okay, now when I hit this right lobe, right, I said that's going to correspond to vapor. The left's going to correspond to liquid. How do I know that? Well, I know that the molar volume, right? So by molar volume or specific volume, that's going to be the volume per mole or volume per mass of a substance. Okay, the specific volume or molar volume of a vapor is going to be larger than the molar volume of a liquid. Right? In a liquid phase, those molecules are going to be closer together. Okay, so as I draw this isobar, okay, I know this is going to be the vapor, all right, and this is going to be the liquid. Why? Because I know that the specific or molar volume of my vapor is going to be greater than my liquid. Okay, cool. Okay, so this is characteristic of my phase boundary. Okay, underneath I have a two-phase liquid. Okay, well, what do I have outside of it then? Well, okay, first I want to look at one more reference point before we kind of jump to that. Okay, and what I want to look at outside here. Okay, and I should mention, right, I said if I specify my volume and it puts me underneath my dome, I know I'll have phase splitting. So I want to remind you, Gibbs phase rule. If I have a single component two-phase system, I have just a single degree of freedom. All right, so molar volume, right, would be enough to pin down the state of my system. Right, and so how do I find the pressure? Well, I draw my isotherm across, or isobar across, and read off my liquid and vapor volume. All right, so here we're plotting pressure versus volume. Okay, what I have depicted here, or what's listed here, is T1, T2, Tc, T3, T4, and so on and so forth. These correspond to lines of constant temperature, or isotherms. Okay. So these lines drawn here correspond to isotherms. Okay, so those are lines of constant temperature. Okay, and going from T1 to T4, okay, this is going to correspond to increasing temperature. Okay, all right. So, we'll touch at how we kind of get to that in a second, right? But these are going to be lines of increasing temperature. And so one key thing to note is when I look back here at this point D, you'll notice, right, if I'm on, say, isotherm 2, when I hit my phase envelope, right, that isotherm is horizontal across the dome. Okay, why? Because my two phases of coexistence are at the same temperature and are at the same pressure. Okay, cool. All right. So now, to the left of my dome, okay, so we said, this left lobe, this left side, that's where I read off my liquid volume. Okay, to the left of the dome, okay, so if I'm outside my dome, I'm going to have a single phase, right, and it's going to correspond to a liquid. Okay, when we talk about our liquid phase, we typically call it either subcooled or compressed liquid. Okay, how do we come up with that name? Well, if I'm here at this state L, which we have labeled on this isobar. Okay, so at point L here, I have a saturated liquid. Okay, and I see now that I've pointed out these isotherms. I'm sitting on this isotherm 2. Okay, well, if I remain at this pressure, so if I keep pressure constant, okay, so I'm at a saturated liquid here at this pressure PA. Okay, if pressure is held constant, but I decrease the temperature, that would correspond to jumping to the left to this next isotherm here, T1. Okay, so I keep pressure constant, but I decrease temperature from T2 to T1. Okay, so if I decrease my temperature from T2 to T1, that puts me in the liquid region. Right, to the left of my liquid lobe, I have a pure liquid. Okay, we call it a subcooled liquid. Why? Because compared to that saturated liquid, I need to decrease the temperature at constant pressure. Right, I need to cool that liquid down. right? This corresponds to a cool liquid relative to the value at compared to saturation at the same P. Okay, so this is my subcooled liquid region. Okay, if I have a single component, single phase system, I have 2 degrees of freedom. All right, so in terms of pinning down my state within this liquid region, I need 2 degrees of freedom, say pressure and volume. Okay, cool. If I go through the same thought exercise on the right, okay, we call this a superheated vapor. Why? If I'm at point V, okay, and at point V I have a saturated vapor. Okay, if I keep pressure constant and I move to the right, move to say, or increase my temperature to move to that next isotherm, right, I'm moving into that vapor region, right, that single phase vapor region. So compared to my vapor at saturation, keeping pressure constant, I need to increase temperature, right, so it's superheated, right, I have to heat it up relative to the corresponding value at saturation. All right, so to the right over here, we have what's called a superheated vapor. Okay, so we have a single phase vapor region over here. To the left, here on this phase diagram, I call this subcooled liquid. It's equivalent to compressed liquid, and we'll get to that name on the next phase diagram. Okay, cool. All right, hopefully making sense. Okay, so looking at the isotherms here for a second. Okay, so one, right? So if I look at my subcooled liquid region, so let's look at say T1. Okay, so my isotherm is nearly vertical, right, in the subcooled liquid region. Okay, it's nearly vertical, right? So equivalently, if I had plotted molar volume versus pressure, that'd be horizontal, right? Or the slope of that line would be essentially 0, right? And so what this tells us, right, if I were to look at it in the opposite way, right, we'd have essentially that dV dP at constant T, right, is equal to 0, right, if it's a horizontal line. Okay, so that's characteristic of a liquid phase, right, well removed from the critical point where we'll mention next, right, and this is just the molar volume changes very little with respect to pressure at constant temperature for a liquid, right. So for a liquid, the molar volume or the density we know changes very little with respect to pressure at constant temperature. Right, in a liquid, the molecules are already close together, so as we apply pressure, there's only so much closer that they can get. Okay, so one way to identify that this is a liquid as well is when I look at the isotherms, they're nearly vertical over here in the liquid region. Okay, all right. Compare that to my vapor region. Okay, in a vapor, right, the molecules are much more, the liquid's much more, or the vapor phase is much more squishy, right? And so if I look at the isotherms over here, right, the slope, is no longer vertical, all right? So I'm, obtaining a finite slope, right, because my compressibility is no longer, 0, right? My volume in my vapor phase is going to be a function of pressure at constant temperature. As I apply pressure to that vapor phase, right, I can push those molecules closer together. Okay, so while liquid, right, we get this characteristic that we can assume that my liquid is essentially incompressible, that volume changes little with respect to pressure at constant temperature. The same is not true over here in my vapor region. All right, so now in terms of identifying, we're saying, hey, temperature is increasing as I go from T1 to T4. All right, so here is my saturated liquid. Okay. Here is my saturated vapor. Okay, so my 2 lobes, right, meet up at a point up here at the top of my dome. Okay, where my saturated liquid lobe and saturated vapor lobe meet, right, at this point, right, we call this the critical point. Okay, and so the critical point, right, so this is going to be at some given. Well, here we can use PC and VC, or it's common to use PC and TC if I look at this isotherm TC corresponding to the critical isotherm. Okay. And so if I draw this horizontal line over, right, this would correspond to PC. Okay. So my 2 lobes meet at the critical point. Okay. Here's my critical isotherm, labeled as TC, corresponding to my critical temperature. For temperatures and pressures greater than PC and TC, which would correspond to this region up here, okay, we call this our supercritical fluid region. So the idea being is while I'm to the left of my saturated liquid region, I have a single phase liquid. To the right, I have a single phase vapor. Okay. In this supercritical region, I have a single phase, and we call it a supercritical fluid because it has both liquid and vapor character. Okay, so when have a temperature above Tc and a pressure above Pc, it puts me in this supercritical fluid region in which I have a single phase. Okay, only a single phase can exist, but it has both liquid and vapor character, if you will. So in terms of increasing temperature, right? So what I'll know or notice is that in this liquid region, right? So here again we're looking at P versus V, right? So vertical line would be incompressible, right? So the slope begins to decrease, right? Deviate from that vertical limit as temperature increases. As temperature increases, okay, the liquid becomes more compressible. Okay, and so you can definitely see it's more compressible at the critical point, and then beyond, Tc, right, in which I have either supercritical fluid or superheated vapor, right, I'm going to have a compressible fluid. Okay, so just by looking at the slopes here, right, and how it's, decreasing, right, until I hit the critical point, right, I pick up in that, hey, this is low temperature compared to high, right, increasing temperature. All right, the last reference point, last two reference points last two comments I want to point out in this phase diagram is something that we'll, leverage later on when we start to talk about cubic equations of state, is have a look at our critical isotherm, right? So our critical isotherm is our isotherm labeled with Tc. So our critical isotherm does something special, if you will, okay? What I want to point out is that if I follow my critical isotherm, is at the critical point, okay, first I see that my first derivative is 0. All right, so at my critical, so if I follow my critical isotherm, okay, first thing to look at is that my first derivative is 0 at my critical point. Okay, all right, so it'd be my first derivative is 0 at my critical point. Okay, second, okay, looking at my critical isotherm, my second derivative is also 0, right? I have an inflection point, right? So here I'm concave up, right? So from calculus, right, my isotherm could say hold water, and then past my critical point is concave down. Okay, so the first and second derivative of my critical isotherm are both 0 at the critical point. Okay, we're going to leverage this later on when we introduce van der Waals equation of state of having two reference points that we can make sure our equation obeys. Okay, so cool. Okay, two other things I want to point out is one, right, it's mentioned in the reading that all fluids approach, our ideal gas state and the limit that P goes to 0 or V goes to infinity at constant temperature. So what that would correspond to, right, constant temperature, you could follow any isotherm. So if you look down here, right, the limit that P goes to 0 or V goes to infinity, right, if you were to extend this diagram out far enough, you'd find that all of these, kind of converge at that, common reference state. Okay, you already kind of see it here. Okay, so all fluids approach ideal gas behavior, and the limit that P goes to 0 or V goes to infinity at constant temperature. So if you were to extend this out, we could see all of those values coinciding at that common value. And then that's critical point, ideal gas limit. I suppose that should be okay. If anything comes up, we'll flip back and think of it. Okay. All right, so next is PT graph. Okay, so looking at a three-dimensional surface, right, here's PV. Okay, next we're just looking at this plane over here. Okay, pressure versus temperature. Okay, the main big difference you're going to see is in our PV phase diagram, we had a dome. Why? Because when I'm at vapor-liquid coexistence, okay, my liquid and vapor at equilibrium are going to be at the same temperature and the same pressure. Okay, but my liquid and vapor aren't at the same molar volume or specific volume. We know that the molar volume or specific volume of my vapor is going to be greater than my liquid. When I look at a PT phase diagram, Okay, I don't have a phase envelope. I don't have a dome. Okay, I don't have a dome. Instead, I have a line. Okay, so what I have here is a line. All right. So actually, my saturation curve for pressure versus temperature is an exponential relationship, but that's not something that we'll derive or work out in this course. Okay, we'll revisit this later on. Okay, but we have an exponential relationship between pressure and temperature. I don't have a dome here. All right, instead, I just have a saturation curve. Okay, the reason being is if I'm at vapor-liquid coexistence, my liquid and vapor are at the same temperature and at the same pressure. Okay, so I don't have a dome. The dome results because at coexistence, the molar volume or specific volume of those two phases are different. Okay, so here's my P versus T plane. Okay, here I have an equilibrium line. Okay, reference points up here. It's C, where my line terminates. That's going to correspond to my critical point. Okay, you also have a reference point down here that is included in the diagram, F, corresponding to my triple point, where I have solid in equilibrium with liquid and equilibrium with the vapor. All right, and then you likewise have this equilibrium curve here between my solid and liquid phase, but we won't get into that here. Right, our focus here is going to be on vapor-liquid coexistence. Okay. All right, so I have pressure versus temperature. Instead of a dome, I have a line because at equilibrium, the temperature and pressure of my two phases are the same. Okay. Now, in our P versus V phase diagram, we drew isotherms. Here we're going to draw isochores. Okay, so an isochore are lines of constant temperature. Okay, so these dotted lines here correspond to isochores. And those are going to be lines of constant volume, right? Molar volume or specific volume. Cool. All right. So if I'm on my P versus T phase diagram, so let's just say I'm on this point here. I can't tell if it's L or V, right? Doesn't matter. V. Well, so if I'm on this reference point, which they have labeled. Okay, so if I'm at this point, so if at this temperature, if I specify, say, temperature and pressure, and I find myself on the line, all right, that tells me I have vapor-liquid coexistence. I have a system at vapor-liquid coexistence, all right? Or equivalently, if you're given a pressure and told you're at two-phase coexistence, all right, I would just draw an isobar to where I found myself on my coexistence curve, and then that would pin down the corresponding temperature. Okay? Because again, if I have a single component two-phase system, I have just a single degree of freedom. So if I specify the temperature and I'm two-phase, right, that tells me where I am on this phase diagram and then would pin down pressure, which I could read off by drawing an isobar. If I specified pressure and said I was two-phase, right, that would tell me where I am on this phase diagram, and I could draw an isotherm and determine the temperature. All right, now, rather than thinking kind of, it's still kind of to the left, right? But, think to the left or, above, right? So above my phase diagram. So here I have a vapor and liquid coexistence on this line. Above that line, I have a liquid. Okay, one way you can think of this is high pressures, right, favor liquid phases. Right, so above. All right, so if I were to keep temperature constant but increase pressure, all right, that's going to favor a liquid. That's going to be this liquid region up here, all right, above my phase equilibrium line. Below my line, I have a vapor, right? So if I were to keep temperature constant and decrease the pressure, that's going to favor a vapor phase. Okay, so above I have a liquid, below I have a vapor. Okay, so now naming. So in the last, in a PV phase diagram, we called it a subcooled liquid, right? You could also think of it as a subcooled liquid here, okay? But it, here sometimes it's called compressed liquid. How do we come up with these names? Well, let's just think. I'm at this point here, all right, on my phase diagram, all right? So I have a system at vapor-liquid coexistence, okay? Well, how would I think about this, or how do I get this name compressed vapor? Okay. And how do I get subcooled liquid out of this? Okay. The first thought exercise is I'm at this point, okay? I'm going to keep pressure constant. So if I keep pressure constant, but I decrease temperature. So if pressure is held constant, but I decrease temperature, that would correspond to moving to the left along this isobar. All right. This horizontal line is an isobar, right? It's a line of, a fixed pressure, of constant pressure. So if I keep pressure constant, if I'm at this state and I keep pressure constant, but I decrease temperature, that'd correspond to moving to the left along this horizontal line. Okay, so decreasing temperature would be the same as, you could think of it as cooling off your liquid relative to that state at coexistence, right? Which leads to the name of subcooled liquid, which is how we labeled it on the PV phase diagram, because that leans in to our thought exercise there. Okay, that's equivalent to compressed liquid. Right, here's this name, compressed liquid. How do you get compressed liquid? Well, I could think of the other process, right? The other thought exercise. So I'm at this point here, right? At two-phase coexistence, vapor-liquid coexistence. Let me draw a line corresponding to constant temperature, right? So this should be perfectly vertical. Right? So if I had some vertical line, which corresponds to a line of constant temperature, the idea now is if I keep temperature constant and I increase pressure, right? If I keep temperature constant but I increase pressure, that would correspond to moving up along this vertical line, right? Would correspond to compressing my liquid, right? Which would lead me to, this compressed liquid region, right? So compressed liquid, subcooled liquid are both the same, and they correspond to a state in which we have a pure liquid, right? A single phase liquid state. Okay. Sometimes when we solve problems, we might even drop compressed liquid and subcooled and just call them liquid, but there you have it. Vapor region is still typically called my superheated vapor region. Same thought exercise. Here's my isobar. All right. If I were to keep pressure constant but increase the temperature, that corresponds to moving to the right. Increasing temperature, I'm heating my system up, right, to this superheated vapor region. Cool. So I have a line because liquid and vapor at equilibrium are at the same temperature and pressure. So I have a line, not a dome. Okay. Above, I have a compressed liquid. Below, I have a superheated vapor. You can go through the same thought exercise in terms of determining phases. And again, I often think high pressures favor liquid, low pressures favor vapors in terms of figuring out where I am on my phase diagram. Okay, and then same thing for temperatures. So if I have my systems above TC and PC, all right, that's going to correspond to supercritical fluid. Right, and so now it's a nice rectangle because this is pressure versus temperature. Okay. These lines correspond again to isocores, lines of constant volume. All right, the last phase diagram we want to introduce is a Z versus P graph. Okay, now where does Z come from? Right, we're talking about pressure, volume, temperature. Right, it said PV and T are our favorite thermodynamic properties to work with or deal with. So here we're going to introduce Z. Z is my compressibility. So Z is defined as being equal to PV over RT. Okay, so Z isn't really a new property, all right? It's related, directly to, our favorite quantities: pressure, volume, and temperature. Okay, so we'll enjoy working with Z later on when we work with cubic equations of state, or just in terms of numerically trying to model data altogether. All right, and so kind of to jump forward, right? The big advantage of working with Z is going to be is that Z is dimensionless. Okay, the value of Z typically varies between 0 and 1. All right, and so if I'm trying to model vapor and liquid in coexistence, right? It's nice having a quantity where my vapor value is going to be, say, close to 1. My liquid will be much smaller but greater than 0. Right, that's a very small range, right? I'm going to have a dimensionless number which varies essentially between 0 and 1. Whereas if I'm trying to model something like volume instead, if I directly use V, now I have units to worry about, and the magnitude of the difference between the volume of my liquid and vapor is going to be significantly different. Okay, so Z really comes in for convenience, if you will. Okay, so we're just defining some new auxiliary property, Z, which is defined as PV over RT. Okay, so here we have a plot of compressibility, Z versus P, so Z versus P. So again, characteristic, just like a P versus V phase diagram, is we have this dome. Okay, we have a dome because the compressibility of my liquid and vapor are not going to be the same. Right, the volume of my liquid and vapor aren't the same. The compressibility aren't going to be the same. Okay, so now the top lobe of this dome, right, is going to correspond to my saturated vapor. The bottom region of this dome is going to correspond to my saturated liquid. Okay, how do I know? Right, well, here I have a compressibility of 1. Right, here I have a compressibility of 0. So this is decreasing Z. Okay, higher Z is going to correspond to your vapor. Lower Z is going to correspond to your liquid. Okay, so we know that the equation of state of an ideal gas is PV equals RT. So I should point out, right, whenever we mention V, okay, V is my total volume divided by the number of moles, right, the moles in my system or mass in my system, right. So V in my equation of state, my ideal gas equation of state, corresponds to my molar volume. Okay, I only mention that because in chemistry I remember PV equals nRT. Here it's just PV equals RT because V is V total over N. So anyways, for an ideal gas, right, in the ideal gas state, I know that PV equals RT. All right, so in an ideal gas state, Z is equal to 1. So here, right, this limit here of Z equals 1, right, will correspond to, this limiting case of an ideal gas. So Z's closest to 1, those larger Z's are going to correspond to vapor. Z's closest to 0, the smaller Z's are going to correspond to my liquid state. Okay, but again, it's an auxiliary property that we're introducing for convenience later on. Okay. Hope that helps. In the next set of notes, we'll get set up and start talking about quantitatively measuring PVT phase behavior of fluids.